anybody think of a parabola in real life? You ever seen one? Can't think of one? Say it again. Oh, the St. Louis Arch, the Golden Gate. Yeah, or not the Golden. Yeah, the gateway to the west, I think is what they call that arch thing. Close. That is slightly different from a parabola. It's called a hyperbolic cosine. That's a whole different story. But you're on the right track. Yes?
You know, in Missouri, the little, I don't know what it's called. It's a baseball thing. Well, in Missouri, they have like that little. I'll look it up.
You mean the one that Jarvis just said?
Did you say that?
Yes. The arch in St. Louis?
Yeah.
Yes. Called Gateway to the West. Yes. But technically, it looks like a parabola, but technically, it's something. The shape is called a hyperbolic cosine. But you're on the right track. All right. Okay, Connor, think fast. That was just a parabola right there. Okay, the path that anything that's thrown through the air takes is a parabola. Okay. Ooh, that was a parabola that did not have very high arc. Okay. Drinking fountain. Okay, water sprays out of a hose or a drinking fountain, goes up, comes down, any kind of fountain, anything that is put in motion. See, that's why the St. Louis one is not, because it's not moving, it's not in motion, it's just that's why it's called a hyperbolic cosine. But anything that's moving, so you kick a football for a field goal, or you hit a home run, or you hit a pop fly, that's all parabolas. Okay, anytime Dakota spikes it, the path that ball is taking is a parabola. Okay, her parabola is going down really fast and really hard, but it's still the path of a parabola. So anything that's launched into the air affected by gravity is going to be a parabola. So there's a formula for the way gravity makes things into a parabola, and here it is. So parabolas pulled by gravity. It's the gravity that makes something that is thrown up come back down, or something that's launched down to go down even faster. And it goes like this. The height is negative 1/2 of gravity based on the time it's in the air squared. Anything squared is a parabola, by the way. Plus v times the time plus h sub 0. All right, so we've got a bunch of variables going on here. So you got to know what each of the variables stand for. Okay, g is gravity. Gravity is a constant, but it depends on what units you're using. Gravity is either 32 if you're using feet, like we do in the United States, or it's 9.8 if you're using meters, like the rest of the world. I think there's only one other country in the world that uses feet besides us. We're a big one, but it's not very common. Okay, V stands for velocity. And it's the initial velocity. Okay, the initial velocity is, if you watch baseball, they talk about the launch velocity, the exit velocity. Okay, the exit velocity, that's the velocity that it starts with. Velocity doesn't stay the same, it's always changing because gravity is going to change the velocity, but it's what the velocity started with when it was first put into motion. And then the last one is height, and it also has a little 0. We could put a little 0 by the velocity too if we wanted. That's the initial height. That's how high it was when it first was put into motion. So sometimes things are put into motion low and they're launched and they go up and then down. But sometimes we're high and we're throwing something down, so that initial height is higher. But that's initial or beginning, or the starting height. T stands for time. So both of those T's both represent time. And the time could be measured in in minutes or seconds or hours or days or whatever, but it's always representing time. So parabolas pulled by gravity are going to follow an upside down model. That's why we have the negative there, because gravity will pull things upside down. So it could look like this and be like perfectly symmetric. Or maybe you're jumping off of a diving board, and so you start up a little higher and then you end up landing. So maybe it's a part of a parabola like that. Or maybe you're hitting something and you're starting at it's just going straight down like that. So the parabola comes in different pieces. It can either be a full parabola, it can be a partial parabola, it can be a half parabola. It all depends on what the initial height is. And so in this case, the initial height was down at the bottom. We might call that 0. Here, the initial height might be a little higher. Maybe it's going to be 8. Okay, this one, the initial height might be a little higher yet. Maybe that's 12. It all depends. Whatever the problem tells you is the initial height, you're going to put that in as your initial height. We also know the initial velocity. Now, like I said, the velocity always changes. So I think it is probably going to be important that you put a 0 here by this original velocity. Whoops. Because that's the velocity at the beginning. Velocity changes over time, and so that gives us our second equation, which is v for velocity. And the velocity is plain old negative g, not negative half g, but negative regular g, times t, without the square, plus v sub 0 without the time. So it's similar to the height equation, except you lose the initial height and you lose the single time, and you lose the time squared. Okay, and that's called the velocity equation. So if we know those two equations, we can answer some questions about a real life situation. So let's keep those two formulas in mind. Maybe put stars by them or arrows or something. Those are going to be your two important formulas. You'll either be, you feeling okay, Lauren, today? Okay. Sometimes I know you start the day with a headache, and at least I do. No good. You'll have your notes, so you don't have to memorize these formulas. So on the open note quiz, you'll have your notes to look at, and then on the real quiz, I'll type the formulas for you. Okay, so you don't have to memorize them. The only one you got to memorize is negative b over 2a. You got to memorize that part, but you won't have to memorize these gravity ones. Okay, so let's do an example. Let's just start with an easy one. Let's say we're tossing a ball in the air, throwing a ball. And we're going to throw a ball from initial height okay, so imagine it's a little kid. Little kid's about this tall, like Jack Price or something like that. Okay, and he goes to throw the ball. You think you're little Jack. Okay, about how high off the ground do you think this is about, approximately? Give me an estimate.
4 feet.
4 feet? Okay. So we'll say he's throwing it from initial height of 4 feet. And the ball leaves his hand with an initial velocity. Okay, and the initial velocity, it's going to be 12.25 feet per second. All right, what we can do is if we know that much information, we can write a parabola to figure out how high it's going to go. All right, so let's picture this. You're not going to have to graph these on graph paper, but you should be able to picture it. Okay, little Jack is throwing a ball from 4 feet, more or less, and it's going to go up, and then it's going to come back down. And it'll hit the ground down here. We want to know, how high is it? Okay, well yesterday we learned the vocab word for that. What's that position called? The vertex. So we want to find the vertex. So first we have to write parabola formula for this. And so the height of this parabola is going to be -1/2 g t squared plus v sub 0 t plus h sub 0. And you have all the numbers that you need. We know h sub 0 was 4, so we'll put a 4 back there at the end. We know that the initial velocity is 12.25, so we can put that in. We know that in front of that is going to be a t squared, and then we need a number for g. So there are 3 numbers you need to put in: the h sub 0, the v sub 0, and you got to put in the g. Now I told you g is always one of 2 things. It's either 32 or it's 9.8. It just depends on the units of the problem. 32 is what you use if the problem is a feet. Okay, so if you're in the United States. 9.8 is what you would use if you're measuring in meters. So this time we're going to use the 32 for the gravity. So we'll have -1/2, and then I'm going to put 32 in for gravity. And so I'm going to clean this up a little bit. So this is going to make -16 t squared plus 12.25 t plus 4. And that is the equation for the parabola we just created. I can use that parabola with what I know yesterday about how to find the vertex. The vertex is h and k, and so now that I've made the parabola myself, I need to figure out what is the position of the vertex. Because the vertex is going to help me know how high this went. And remember that yesterday is -b over 2a for the vertex. That's why I asked you to get your calculator out. So hopefully you have that on your desk. -b would be -12.25 over 2a would be 2 times -16. So that's going to work out to be -12.25 divided by -32. So if somebody who has a calculator handy can tell me what that works out to be, that would be great. Has anybody got that? -12.25 divided by -32. It's going to be a decimal, and that's okay. Perfectly? 0.38, or are you rounding that? Okay. Can you give it to me in a fraction? You know how to turn it into a fraction on your calculator? Press the math button and then number 1. Okay, 49 over 128. Okay, that's part of the vertex. How do I find the second half of the other part of the vertex? Okay, plug it in where? For t. Okay, so then we'll have -16 parentheses 49 over 128 squared plus 12.25 times 49 over 128 not squared plus 4. Okay, so those of you who have your calculator out, can you find that? Sam, trust me, you're going to need your calculator in a little bit, so might as well have it out. Okay, go ahead and type that in. Make sure you use the negative for 16. Make sure you use parentheses around your 49 over 128, and then let's hear how high little Jack was able to throw this ball. Okay, so let me know when you get it. Maybe if I could have a couple people working on it, that way we could confirm whether it's right or not. What'd you get, Ben? 6.34 feet. Dakota, did you get something? You got the same thing? Diego, did you get it?
Yeah.
Same thing. Okay. 6.34 feet. So not super high for little Jack. Okay. All right. So our maximum turned out to be 49 over 128, comma, 6.34 feet. Okay, and that answers the question about how high it would go. Okay. Any questions about that? So that's where you create the parabola by yourself using the formula for gravity. You can also answer a follow-up question, and the follow-up question would be, when would it hit the ground? When does the ball land? Okay, well, let's think about this a minute. Looking at our picture, remember, I don't have to do a perfect graph, but if I know the initial height is 4, and I know that the maximum height is 6.34, what do I know about the height when it's landing? What about the height at the end? What will the height be? Like literally, it's landing. What's the height going to be? 0, okay? The height is going to be 0 down here when it lands. Okay, so then I can use my parabola equation, and I know that it's negative 16t squared plus 12.25t plus 4, and I'm going to set that equal to 0. And we're going to use what method to solve a problem that's equal to 0? This goes back to, quadratic formula. Either factoring if you can, which I don't think this is going to factor very well, or a quadratic formula. And so the quadratic formula will tell us when the ball lands. So we're going to use the quadratic formula. And so that will be time equals negative b plus or minus the square root of parentheses b squared minus 4 times a times c all over 2a. And so that'll just be some math that you need to use your calculator to figure out. You should be able to figure out what 12.25 squared is. You should be able to figure out what negative 4 times negative 16 times regular 4 is. And do that all with your calculator. I'm not going to finish that. I'm going to let you type that into your calculator, but that's how you would do that. Okay, our second example. So that example was you make your own equation with gravity. The second example is I'm going to teach you how the calculator can make an equation using gravity as well. And that is using the regression feature that we've done before. And we're going to do regressions for parabolas. Okay, could you go to Stat Edit and make sure all your lists are empty? And in your lists, you're going to put your list for L1. So we're going to do 1991, 1992, 1993, 94, 95, 96, 97, 98. And the data that's going to go with that is this. All right, you be typing that in. I'm going to try and catch up to you. All right, hopefully that's enough time. Okay, now you want to set your window. Your window, we need an X-min and an X-max. Remember, we learned how to do that. Our minimum has to be smaller than 1991. What should we use? 1990. Okay, your maximum has to be larger than 1998. What should we use? 2000. Okay, what's the difference between 1990 and 2000? 10. So what should our scale be? If it's just 10, it should just be 1. Okay, our Y-min has to be smaller than 1, or smaller than 1.04, so what should we use? Okay, 0, or I could just use 1, because these are all decimal numbers, and my Y-max. I could use a number that's larger than my largest. My largest is 1.8, so what should I use? 2. Looks great. And a good Y scale for that when you're dealing with decimals is 0.1. And then make sure your Y equals is clear, and then you should be able to graph it. what the formula for this parabola is. This is called a regression. And so we're going to go back to stat now that once you've created your parabola, you go back to stat. This time we go over to calc, and we're going to use a different regression than we used last time. There's lots of different regressions. We'll cover them all, or most of them over the course of the year. Before, last chapter, we used number 4, which was for lines. This time we're going to use number 5. Number 5 is for quadratic. Quadratic formula, quadratic expression, quadratic regression. Quadratic means parabola. But notice that there's a cubic, there's a quartic. Cubic would be if it looks like a snake shape. Quartic, okay, that's going to be the next shape that we're going to do. Let's start with quadrate. It should be set to list 1 and list 2, but remember when you get to the reg EQ, you need to put, use a vars. Use your vars command, your yvars, and pick the first function. If you don't do that, it will not graph the parabola for you. So make sure you don't skip over that part. And then calculate. And there you go. It just will tell you what the stretch is going to be. It tells you the A is the stretch. It tells you the B, it tells you the C, and it tells you the R squared being 99.999, super, super strong. This is an awesome parabola. So I'm going to copy it down in my notes. You should copy that equation down as well. Negative 0.053 x squared. Actually, I wouldn't mind if you use t squared, but because it's time instead of x. 219t minus 21930. And then when I graph it, it should go right through those parabola points just about perfectly. Let me go back to my screen here. Okay, do you see how I wrote down the parabola? T stands for time. And that's the rest of the equation. So now, yeah, Ashley? 0.055. Did I just copy it wrong? 0.055, sorry. There we go. Okay, so I can use this to predict other years. My years stopped at 1998, but now I could do 1999, or I could do 2000. If I wanted to do 1999, I just put 1999 in for the time, here and here. I could put 2000 in. I could put any number I wanted in for the time to figure that out. When do you think the maximum happens? If you look at the data, approximately, when do you think the maximum happened? What would you guess? Where's the highest number there? 1995. Okay, that's what we would approximate. We can figure it out exactly using negative b over 2a. So negative b over 2a would be negative 219 over 2 times negative 0.055. And if I figure that out, that will tell me exactly where the maximum is, rather than just having to guess. And it turns out to be, oops, yeah, pretty close. Okay, when it worked out, yeah, our estimate was correct. Let's see, what else could we tell? Oh, I know what I want to show you. Okay, we know that our numbers started at 1.04 and they went up to 1.8 and then they started going back down again. What if I want to know when they cross 1.25? Okay, when did the numbers cross? Oh, let's do 1.5. When would they cross 1.5? Go to y equals and put 1.5 in your y2. Don't erase your y1. Put it in your y2. And graph that. And now you can tell where 1.5 is. And I can figure out where it's going to cross 1.5. And we did that with second trace. All these things we learned in the other chapters are coming back again. So we'll do second trace. We'll do number 5, which is intersect. We'll use our left and our right arrows to follow the curve to the intersection point, and we'll hit enter so that we can find that intersection spot. And it tells me in 1992, 0.362, that's when it's going to cross the line of 1.5. But it crosses the line of 1.5 again on the other side, because it goes up past 1.5 and then it's going to fall below 1.5. So we could figure out the other one as well, doing second trace, number 5, and use your right arrow this time to get us sitting over closest to that intersection spot. So I'm following the curve to right there. And it tells me that that happens in 1997. So in 1992, it got above 1.5, and then in 1997, it gets back below. So a situation where this might happen might be like the housing market. Okay, the value of your home goes up and up and up and up and up, and it passes a certain point, and then it gets to the max. And then something happens, and the value of your home starts to go back down again. Okay, and then hopefully you're hoping it'll go back up eventually. But this happens all the time in real life. Or maybe you have a stock, and your stock is going up for a while, and then it starts to go back down. Okay, so the trick is to figure out where the max is. That's the best for you, is to figure out that max spot.